Hello, everyone, and welcome to Lecture 8 of GPU computing. Today, we're going to start talking about parallel patterns, and the first parallel pattern we're going to talk about is convolution. So before that, let me review what we've covered so far. We have quite a few lectures so far, and we've been talking about the fundamentals of GPU computing. So before I transition into this new part of the course where we're talking about parallel patterns, let me just do a quick review. So far, we looked at the beginning of the course how how a single thread performance has stagnated because frequency has stagnated because of the power wall, and this led to this move towards parallel computing. And we also looked at the difference between the design of a CPU, which is a latency-oriented design, and the design of a GPU, which is a throughput-oriented design. And we saw how in latency-oriented design we focus on making one task as fast as possible, and that includes using powerful ALUs, large caches, so that the latency the memory operations are as fast as possible, so that we have less likelihood of cache misses. Sophisticated control flow that we can do things like branch prediction and data forwarding to minimize pipeline stalls, and we have a little bit of multi-threading to hide the little bit of latency that's left, that's not hidden by hidden by these other techniques. On the other hand, in GPUs, we have throughput-oriented design, where we have smaller ALUs, so an individual arithmetic operation will take much longer. However, we have many of them, and this gives us more throughput. And we saw how we have smaller caches and simpler controls so that we can dedicate more area in order for us to perform more computation in parallel. And we compensate for having this high latency in our operations by having a massive number of threads to hide the latency. And then we looked at a typical GPU in a system and how it interacts with the CPU. We said that usually we have a CPU with main memory, we have a GPU that has its own device memory, and we usually copy data, allocate memory on the GPU, and we copy data from the main memory of the CPU to the memory on the GPU, and then we execute our kernel on the GPU while accessing memory from GPU's memory, and then we copy the data back, and then we deallocate the GPU memory. Of course, there's other ways like unified memory where you just allocate data on the CPU and use it on the GPU, and we'll talk about these kinds of things later. But this here is one of the ways that people typically use GPUs. And we started off with a simple vector addition kernel where we looked at data parallelism, and we saw how data parallelism was suitable for GPUs, and the hello world of data parallelism was vector addition, and we saw how our grids are organized into threads and blocks, and how we can calculate the index of the thread and use that index to perform an operation, the same operation in each thread on different pieces of data. We then looked at how grids are actually organized into multi-dimensional arrays of threads. So we can have 2D grids, we can have 3D grids. And we also looked at how multidimensional data is typically laid out. We said it's laid out in row major order. And we saw how when we access multidimensional data, we need to do this index calculation in order for us to convert a two-dimensional index, which we usually obtain from our threads, to a one-dimensional index in order for us to access our dynamically allocated arrays. And we did multiple examples of this. We did RGB to grayscale conversion. We did image blur, which is a special case of convolution, which we're going to be talking about today. And we also did matrix multiplication. And this example actually stayed with us for the next few lectures. We looked at other kinds of optimizations that we can apply. After having gone through these basics of the the CUDA programming model, we then switched to talking about the GPU architecture, and we saw how it's organized into multiple SMs, each having multiple cores that share memory and control, and all the SMs have access to the same global memory. And we said that when grids are scheduled on SMs, they're divided into blocks, and at the schedule of the SMs at block granularity, which means that all the threads in the same block will run on the same SM at the same time. But of course, we can have multiple thread blocks running on the SM simultaneously. We also said that when blocks are scheduled on SMs, they're divided into warps, and the unit of scheduling is warps. And the special thing about warps is that threads in the same warp execute following the SIMD model, which means they all execute the same instruction on different pieces of data. And the warp size has been 32 since the beginning of GPUs GPUs were introduced. But of course, this may change in the future. It hasn't, but it may, so you shouldn't just assume that the warp size will always be 32. Now, having seen that warps execute in SIMD, this brought up the issue of control divergence. We said that if we have threads in the same warp that each want to take a different control path, so I can have an if statement, some threads want to execute the then part, some threads want to execute the else part, then because all the threads must execute the same instruction, what happens is that they first all go to the then part, and then the threads that took the will execute while the others remain inactive. And then they all go to the else part, and then the threads that took the first branch will be inactive, while the threads that took the else branch will execute. And we observed that when we have this kind of thing, these inactive threads are occupying cores, but they're not doing anything. So this results in underutilization of our hardware, and we said that we would like to minimize this, and we will see examples of how to do this in future parallel patterns that we'll talk about. We also spoke about latency hiding, where we said that by having many more warps and many more threads scheduled on an SM than the number of cores that we have on the SM, what we can do is we can benefit from this oversubscription of threads to SMs by whenever one of the warps encounters a long latency operation, we remove it and we bring in another warp to execute in its place until, and then we keep bringing in new warps until the original warp finishes its long latency operation. And by doing this, we're able to hide the latency. And because we're interested in having many threads scheduled on the SM, in order to hide latency, we said that we have this notion of occupancy, where the number of threads, the maximum number of threads per SM is some number depending on the device. For example, on the V100, it's 2048. But there's other things that might constrain my occupancy, such as how many blocks I can have per SM, or how many registers each thread the SM has, or how much shared memory the SM has. And we spoke about the importance of being aware of our resource utilization in order for us to ensure that we maximize the number of threads on the SM. Next, we looked at memory in the GPU architecture, and we saw how threads on the same cores on the same SM have access to this shared memory. And we saw how we could use this shared memory in order for us to place data that we plan to reuse. So, for example, in the tiled matrix multiplication, what we did is we observed that rather than having each thread load an entire row and an entire column of A and B respectively, what we did is we had the threads that are in the same block collaborate in loading a tile of A, where every thread that's assigned to one of these output elements will load only one element in this tile. But then the thread that loaded one element of this tile can actually use the other elements in this tile to benefit from the elements that other threads have loaded. So basically, what we do is we load these tiles to shared memory, and then we compute inside of shared memory. And what this does is that it minimizes the number of global memory accesses in order for us to have a better compute to global memory access ratio. Then we looked at the organization of DRAM, and we said that in these DRAM banks, access to the DRAM array is slow, but then once you have the DRAM burst, accessing part of the DRAM burst is fast. So it would be best if threads, when threads issue their memory requests, to be accessing data in the same DRAM burst, because when you access data in different DRAM bursts, you have to go to the DRAM array and then access the data in the burst, and then if the next access goes to a different burst, then you have to go through the DRAM array again, and you have to then access the burst. However, if you access the same DRAM burst, then you read the DRAM array once, and then you serve the data from the burst, and then you serve the other part of the burst, other parts of the burst later on, without having to go back to the DRAM array. And if we have multiple DRAM arrays, then what we can do is we can hide latency by reading while reading from the DRAM array of one of these DRAM banks, we'd be serving from the burst of another one of these DRAM banks. And this is another motivation for us to maximize occupancy on the GPU, because just like maximizing occupancy helps us hide pipeline latencies, it also helps us. It also gives us a lot of memory accesses, which help us hide the memory access latency. And with that, we developed this checklist of common optimizations, such as tuning resources to maximize occupancy, minimizing control divergence, having a uniform access pattern to enable memory coalescing, shared memory tiling so that we can capture data reuse, thread coarsening to mitigate the price of parallelization, and privatization, which we haven't covered and we will cover later on. But choosing which of these optimizations to apply depends on what is the bottleneck that your particular application is experiencing that's limiting its performance. And with that, we spoke about the importance of knowing your bottleneck, because optimizations trade off one resource for another. So you want to make sure that you're trading a resource that you have plenty of for a resource that is your bottlenecked resource. That means that we need to select the proper optimization. And in order for you to know your bottleneck, CUDA provides you with a tool in order for you to profile your application in order to figure out what is being utilized and what is not being utilized, so that you can assess what your bottlenecks are. So this was kind of a breeze through what we have covered so far. This ends our first part of the course on the fundamentals of GPU computing. In the next part of the course, what we will do is we're going to talk about parallel patterns, and we're going to spend quite a bit of time talking about these parallel patterns. And hopefully with each pattern we talk about, we're going to introduce maybe a new architecture feature or a new optimization technique. So the objective of the parallel patterns is to learn about the parallel patterns, but it's also about using these parallel patterns to learn new optimizations, new techniques, or new hardware features. And we will start today with convolution. But before I get started, does anybody have any questions about the overall flow of the course so far? Okay, well, if there are no questions, then today, like I said, we're going to be talking about convolution, our first parallel pattern. And we're also going to be using convolution to introduce a new feature of the GPU architecture and the CUDA programming model, which is constant memory. Okay, let's begin by talking about what a convolution is. So a convolution operation is an operation where you have some input, and the output of the convolution operation is such that every element of the output, and here we have a 2D convolution, every element of the output is going to be a weighted sum of the corresponding input element and its neighbors. Okay, so every output element is a weighted sum of neighboring input elements. Now we've seen an example of this before, right? Exactly. The image blur was a special case of convolution where all the weights were the same. So at the image blur, we went through these input elements and we simply calculated an average. However, image blur is a special case of convolution. In a more general form of convolution, we could have a different weight for each of these input elements. And these weights would be determined by something like a convolution mask. Okay, so we could have some kind of convolution mask. Okay, a lot of times people call this the convolution kernel, but I'm calling it a mask instead of kernel just to avoid using the same kernel to mean multiple things, because we're already using the word kernel to mean the CUDA kernel functions. Okay, so I'm going to call it a mask. So we have this convolution mask, and this mask, it consists of a set of weights. And these weights are applied to the inputs. So I compute a weighted average of these inputs according to the weights in the mask in order for me to get my output. Okay? So where is convolution useful? Well, convolution, it turns out, has many applications. It's commonly used in signal processing, image processing, video processing, and it's usually used to transform signals. These could be one-dimensional signals or pixels, or like in images. So these could be 2D, into more desirable values. So, for example, we can have a convolution that computes a Gaussian blur, which is a more sophisticated blur than the naive blur that we saw before, where the farther away pixels might have less weight than the pixels that are closer to the center. We could have a convolution that sharpens an image, that does edge detection, etc. And the transformation that is done by a convolution operation depends on the weights in the mask. Okay. Now, we are going to be using 2D as an example. It's nice to visualize that it's complex enough. But there can also be a 1D convolution. There can also be a 3D convolution. Okay, so if you have a signal, for example, that you're processing, you might be using a 1D convolution as opposed to a 2D convolution. But we'll be using 2D convolution as our example in this lecture. Now, having said this, what do you think is a good way of parallelizing convolution? So based on what we've done so far, yes, go ahead.
A bit in the same way we did for matrices.
Which is?
Basically, we break up the images into two sets of matrices, and instead of doing multiplication, we just multiply each value together and add them up. Yeah.
Okay, I was actually looking for something simpler than that, which is along the lines of what we did with blur.
One
right?
thread per pixel per output
Right,
pixel.
exactly. It's that simple. So to parallelize convolution, what we could do is we could simply have one thread per output element, okay? And this thread would be responsible for going through the neighboring input elements and the mask and calculating the weighted sum. Okay, so this is a very simple approach to parallelizing convolution. That's not the only approach. There are other approaches for parallelizing convolution. But for today, we're going to go with this approach. Okay? Now, this is a straightforward approach, right? Every thread is responsible for an output element, and you just have a loop that goes through your input and your mask. Now, one thing that you might notice here is that this mask is usually small. So for example, over here I have a 5 by 5 mask. And the mask is the same for all the different threads. So all the threads are going to be accessing a different part of the input, but they're all going to be accessing the same mask. So what we can do in this case, because the mask is small, and because all the threads access the mask, and because another important thing is that the mask does not change throughout the execution of the kernel, what we can do is we can actually store the mask in a special place called constant memory. Exactly, constant memory. So storing the mask, some observations. The mask is usually small. The mask is constant, so its weights don't change. And the mask is accessed by all the threads in the grid. So an optimization that we can apply is to store the mask in constant memory for quicker access. So if you remember, when we introduced the CUDA programming model, we said that threads have access to registers, and then the threads in the same block, each thread has its own registers. Threads in the same block have access to a shared memory, and then all threads in the grid have access to a global memory. Well, it turns out that all threads in the grid also have access to a constant memory. Okay, they also have access to a constant memory. So what we want to do is we would like to put our mask in constant memory, and constant memory is going to be faster to access than global memory, and I'll explain why later on. But for now, let's see how we can access constant memory using the CUDA programming model. Okay, so let's see how we can use constant memory. Okay, so I'm going to switch over here to my code. Make this a little bigger. So over here, I've set up this code for us to implement convolution. So I have this function on the GPU that allocates the input, allocates the output, copies the input, and then it copies. Over here, we need to copy the masked constant memory, and then we call the convolution kernel, and then we copy back, and then we free the allocated memory. Okay. So what we would like to do is we would like to create a. Notice here we have. When we did CUDA-malloc, we allocate memory for the input and we allocated memory for the output. But what we'd also like to do is we would like to allocate memory for the mask. But this CUDA-malloc over here, CUDA-malloc puts data inside of global memory. What I'd like to do is I'd like to put my data inside of constant memory. And the way I can do that is by declaring a global array like this. I can write __ constant __, okay, And I can specify the type of my mask. In this case, I'm going to make it a float. Okay, my input's going to be a float. My output's going to be a float. And then also I'm going to make my mask a float. Okay, and then I can give it a name. I'm going to call it mask underscore C. Okay, just like I use underscore D to say that something is in device memory or global memory, I use before underscore H to indicate that something is in host memory. I use underscore C just as a convention to say that something is in constant memory. I didn't have to do that. I could have just written mask, for example. Okay, but I write mask underscore C just to indicate that something is in constant memory. Okay, and then the mask is going to be a 2D array. So I'm going to specify that it's a 2D array by putting the size over here and then the size over here. And what I've done is I've already specified in this header file what my mask dimension is. So my mask radius is going to be 2, meaning I go 2 in each side, and the total size of the total dimension of the mask is going to be 2 in one side, 2 in the other side, and then 1 in the middle. So that's 2 times 2 plus 1, that's 5. So the dimension of the mask is going to be 5, like we saw in the slides. So here, what I can do is I can specify that this is mask dim by mask dim 2D array. Okay, so this is how we declare an array in constant memory. And now what I would like to do is I would like to initialize this constant memory array. And it's constant memory, which means that we cannot write to it when we are executing on the GPU. But what we can do is we can copy to it from the CPU. Okay, so what I'm going to do is in this convolution GPU host function, I'm receiving this mask array, which is a CPU array, and all I have to do is I want to copy this mask array to the constant memory on the GPU, and the way to do that is as follows. I have a function, a special CUDA memcopy function for copying to constant memory. It's called CUDA memcopy to symbol. Okay, so it's not just CUDA memcopy, it's CUDA memcopy to symbol, which indicates that we're copying to constant memory. And as before, we specify our destination pointer, which in this case is mask underscore C. We specify our source pointer, which in this case is mask, which corresponds to this over here. And then we specify the size of the data that we want to copy, which in our case is going to be mask dim times mask dim. This is the size of the mask. And then the size of each element in the mask is the size of float. Okay. So by doing this, this is how we copy data from the host to the constant memory on the GPU. Okay, and this is the code that we wrote. Now there's a catch with constant memory, and this catch with constant memory is that we can only allocate 64 kilobytes of constant memory. Okay, and this is important because if it wasn't for this, then if you remember our matrix multiplication, our whole input matrix A and our whole input matrix B are constant, right? They don't change throughout the lifetime of the kernel. But I'm not going to go and put my whole matrix A and my whole matrix B inside of constant memory because constant memory, the trade-off is, it's fast, but the trade-off is that we can only allocate a small amount of it, such as 64 kilobytes. Okay, so otherwise we could put our input, but we can't because it's too large to put in constant memory. Now, what's the motivation behind having this constant memory, and why does knowing that it's constant make it faster, and why do we have only a limited space? Well, the motivation is as follows. First of all, when data is constant, it's easier to build an efficient cache for it, right? Why is that? What's the difference between building a cache for data that might change and building a cache for data that is constant?
You don't need to write. You only need to write once.
Right, you don't write to the cache. And what does that mean? What did we have to do when we used to write to the cache?
We used to set bits, valid bits and dirty bits.
Right, we had these dirty bits and we had to do write back and we had to do all these things. So all of that is more expensive to implement, right? But if I have a constant cache, then I don't have to worry about this stuff, right? I'm just building a cache to be read. I'm not building it to be written. so I don't need to support writing to the cache. Okay, so no need to support tracking changes and writing back. Tracking changes using a dirty bit and writing back when there's an eviction. Okay, what else do I not need to support if I cannot write to my cache? And remember, this is a parallel processor.
Thread number and so on.
No. So what happens if I have many threads that are writing to some value?
Multi-access, so it can be accessed by multiple threads at once.
Right. So what happens in my cache hierarchy when multiple threads are accessing the same cache line?
You might get conflicts.
Scheduling.
So there, conflicts, and how do you deal with those? There's something called cache coherence, right? Are you guys familiar with cache coherence? So you need to make sure your caches are coherent. So when you have a cache that you can write to, you need these kinds of coherence protocols in order to make sure that the data that you have is consistent across the different caches. Whereas when some data is constant, you don't need to support cache coherence. Okay, you don't need to support cache coherence. Okay, so then there's no need to support cache coherence. Okay. All right, the other point about constant memory is that it is small in size. And being small in size, meaning that we can minimize evictions. So the cache has low miss rate because the total amount of constant memory that you have is small. So your constant memory can fit inside of your cache. And that is why, even though we saw that from a programming model perspective, all threads have access to the same constant memory, there's actually a constant cache that sits inside of each SM that caches this constant memory, and this constant cache is different from the L1 cache or the shared memory. Okay? Is it clear? Any questions?
Professor, instead of using the constant memory, why, since our kernels are quite small, why don't we just put them into the cache for the SM cache, the shared memory, I mean, and they'll stay in the shared memory because it's the same value that repeats.
You could put them in shared memory, but that means you have to do the work for that, right? So shared memory is managed by the programmer. So you have to go and load mask and put it in shared memory and do all that stuff. But with constant memory, you don't have to do any of that, right? The constant cache is managed by the hardware, not by the programmer. But shared memory is managed by the programmer.
Okay, I see.
Okay. Okay, so having said this, now we've seen how to allocate constant memory, and we've seen how to copy to the constant memory. The next question is, how can we use this constant memory inside of our convolution kernel code? So let's go now and write the convolution kernel. So let's switch back to our code now. And now that we have our mask and constant memory, let's write our convolution kernel. So it's going to be very similar to the image blur kernel, right? We said that we want to have a thread assigned to every output element. So what we're going to have to do is we're going to have to find the row index for that thread and the column index for that thread. So how do we do it? We're going to write int. And what I'm going to do, like I did before with the image blur kernel, is I'm going to distinguish between the output row and the input row, because every thread is assigned to an output element, but it processes multiple input elements. So the thread index is going to be used to calculate the output row. So I'm going to write int out row is equal to, and remember the row corresponds to y dimension, so it's going to be block index.y times block dim.y plus thread index.y. Okay, and then we're going to have int out column is equal to block index.x times block dim.x plus thread index.x. Okay, so now we have the indices for the output row and output column that the thread needs to compute. The next part is the boundary condition. I want to make sure that only the threads that are within the bounds of the input are going to compute. So what do? We're going to compare out row and out column to our boundaries. So we're going to write if out row is less than height and out column is less than width. Okay, so we have all of this. Now what we can do is we can have this thread start computing. So first I'm going to initialize a floating point value sum, which is going to be the accumulator that I'm going to accumulate when I'm calculating the weighted sum. And now what I'm going to do is I'm going to loop through my neighboring inputs and my mask, and I'm going to calculate the weighted sum. Okay. Now, what are my loop bounds? So these loops that loop through my input and my weighted sum. What are the loop bounds for these loops? So if I'm looping through my input and my weighted sum, it's like I'm looping through the elements of the mask. So the loop bounds are going to be simply the dimensions of the mask, which is mask dim. Okay, so I'm gonna write for int mask row is equal to 0, mask row is less than the mask dim. Okay, and then plus mask row. Okay, so now I'm looping through the rows and the columns of the mask, and I write for int mask column is equal to 0, mask column is less than mask dim, and then plus mask column. Okay, so now what these two loops are doing is they're looping over all the elements of the mask. And now what I need to do is I need to find for each mask element what is the corresponding input value that I need to read from. Okay, so I need to calculate in row and I need to calculate in column. Okay, so let me explain how to do that. Let's go back to the image that we had before so that we can explain how to do that.
Professor, can't we avoid having those loops? In the case of convolution, I feel like you can maybe deal with it without a loop. No.
Explain. What do you mean? How do you want to deal with it without a loop?
Yani you have maybe if you have you depend on blocks to iterate through whatever you need. بس ما بعرف if it's
so what do you so right now the way our parallelization approach is to find a thread for every output element. Okay, and this thread is going to loop through our mask and our input and calculate the weighted sum and then store the output value. So I need the loop to loop through my mask, right? So if you want to get rid of these loops, what do you want to replace them with? Do you mean that would you like to maybe assign a thread to every input element?
Maybe something like that, and I haven't completely thought about it.
So are you trying to parallelize these two loops, for example?
Yes.
Okay. Well, you could do that, right? You could do that, but that's only going to be beneficial if you have very little parallelism in your output. Okay. But if this output is thousands of pixels by thousands of pixels, you already have a lot of parallelism from just assigning a thread to every output. So there's no benefit in trying to extract more parallelism by also parallelizing the weighted sum itself. But if your output was very small, such that for some reason, by assigning a thread to every output element, you have not fully utilized your GPU, then maybe it becomes worth considering whether you want to also extract parallelism from the mask by parallelizing these two loops as well. But for typical workloads, your output should be fairly large, such that it's not usually worth parallelizing the mask. In fact, you might even want to apply thread coarsening to have every thread serialize multiple output elements instead of only be responsible for one output element. Okay.
Okay. Thank you.
Yeah. Okay, great. So so let's go back and see what we do. So I have my output row and my output column, and I have my mask row and my mask column, and I want to find the corresponding input row and input column. Okay. So my output row is going to refer to the row of this element over here, which is this row here. And my mask row is going to refer to the row of the mask element that I'm currently processing. So let's say my output row was referred to the row here, and my mask row was 0. So it was this first element, this first row over here. Okay. What's my corresponding input row going to be? It's going to be this row over here, right? So it's going to be the row of the element, the output element, which is here, minus the mask radius. The mask radius here, in this case, is 2. And the mask dimension is 5. Okay? So the input row is going to be the output row minus the mask radius plus the mask row. So if my mask row is 0, it's just going to be the input row minus the mask radius. If my input row is 1, so if I'm finding the input element corresponding to this mask element, that's going to be this input element. So what I would do is I would start from my output row, and then I would subtract the mask radius, and then I would add 1, which is my mask row. Okay? So the mask radius, like I said, it's the number of elements in one direction. So in this mask over here, my mask radius is 2, and my mask dimension is 5. All right. So then the input row is going to be the output row minus the mask radius, okay, plus the mask row. And the same thing for the column. The input column, so in this case, the input column refers to over here. The input column is going to be the output column minus the mask radius, which brings us to the beginning of the mask, plus the mask column. So if the mask column was 0, then it's going to be the output column minus the mask radius. If my output column was 1, and if my mask column was 1, then my input column is going to be my output column minus the mask radius plus the mask column, which is 1. Okay. So then my end call is going to be my out column minus the mask radius plus my mask column. Okay. And just as a reminder, since someone asked what is the mask radius, so I've defined the mask radius here to be 2, and I've just defined the mask dimension in terms of the mask radius. So it's 2 times the mask radius plus 1, which in this case would be 5. Okay. So now that I have my input row and my input column, what I can do is I can accumulate to my sum, right, the multiplication of, remember, I'm doing a weighted sum of the input with the output. Okay, so I'm going to accumulate to my sum the multiplication of the mask element with a corresponding input element. And yes, you're absolutely right that we need to do a boundary check, but let me first do the accumulation. Okay, so you're absolutely right. I need to have a boundary check. Okay, but let me do the accumulation and then show you the boundary check, because it becomes easier to explain the boundary check once we've actually written out the index. Okay, so my sum is going to be sum plus equals mask underscore C of my mask row, mask column. Okay, so then I use the mask row and the mask column to index the mask, times okay? And now I want to index my input, and that's going to be input of my n row, okay, times the width of my input. Okay, so again, I go to my n row, which might be here. I multiply it by the width of the input, and then I add to it the column. Okay, so it's going to be n row times width plus column. Okay? Okay, now what I want to do is I need to have a boundary check because I want to make sure that my input is within bound, right? I could be at maybe, you know, this input element could be over here, so the other input elements could be out of bound. Sorry, my output element could be here at the edge, so some of the input elements could be out of bounds. You know, it could be here out of bounds. So I need to make sure that the input elements that I'm accessing are within bounds. And to do that, remember what we said about boundary conditions. Every memory access needs to have a corresponding check on the indices to that access. Now with mask C, I don't have a problem because I know that mask row and mask column go from 0 to mask dim, which is all within bounds. So mask row and mask column are always going to be within bounds. The checks need to be on the indexes to input, and the indexes to input are basically n row and n column. Okay, so what do I need to check for n row? Well, I need to check that n row is less than height, okay? But I also need to make sure what? I need to make sure that n row is positive because remember, n row is out row minus mask radius. So if mask radius was greater than n row and mask row was 0, this input element n row could be negative, right? So it could be the case that my n row is larger than if I have this element was all the way out here, it could be the case that my n row is out of bounds here, and that's why I need to check that. Sorry, I was referring to the column. So it could be the case that this element is all the way down here. So I need to make sure that my n row is less than the height. That's what I'm doing here. But it could also be the case that this output element is all the way over here. So I need to make sure that my n row is also not over here. So I need to make sure that my n row is greater than or equal to 0. Okay, so n row is less than height, and n row is greater than or equal to 0. Okay, and the same thing for the column. I need to check that n column is less than width, and n column is greater than or equal to 0. All right? So now that I do the boundary check and I do the accumulation, does someone have a question?
Yeah, don't these boundary checks cause control divergence?
Yes, they do.
Okay, so is there a better way to deal with boundary checks?
Well, I mean, you can imagine that. So the amount of control divergence you're going to get is not significantly high because for most of these threads, right? For most of these threads, they're all going to be within bounds, right? But only the few threads that are the edges are the ones where you're going to have control divergence. Okay, so in practice, the control divergence here is kind of inevitable and it's not really worth optimizing for. The real control divergence that you want to optimize for is the control divergence where all the threads are experiencing divergence, and we will see an example of that in a future lecture. Okay. Yeah. Okay, so after we've done this, we've accumulated to the sum. The final part is to store the output element. So we're going to write output of out row times width plus out call is equal to sum. Okay?
Professor,
Yeah.
when you're getting the input, isn't it in row times width plus in column?
Oh, right. Thank you. This should be in column. See, one of the things about programming live when you're teaching a class is that you're bound to make these kinds of bugs. But fortunately, I have many pairs of eyes that are double checking the code that I'm writing. So thank you guys for your continuous feedback throughout the course. Okay, so having said this, let's now compile and run the code and see how well it performs. So I'm going to compile. And I'm going to run. Let's hope for no errors. Okay, there we go. And as you can see, we have quite a bit of improvement, right? The original code, the CPU time is around 2000 milliseconds. And here we have 5 milliseconds for the GPU time and so for the kernel time alone. And if you include the copy time, it's still quite fast, 85 milliseconds. So as you can see, convolution actually performs pretty well on the GPU. Why is that?
Heavy amount of
Because-
parallelization.
Sorry?
You have a very heavy amount of parallelization.
Well, but that's also the case for vector addition. But vector addition does not see as big of a speed up.
Because if you consider the cache behavior, it's gonna just put basically it's like it's doing tiling on itself, and it's not really that much memory bound.
Right, you're right. So we have a lot of data reuse. So if we're lucky, our data is in our cache, and we have good cache utilization. Okay, and also one of our inputs is in constant memory, so that one is fast already. And the other input is in global memory, but the memory accesses are well behaved, right? My memory accesses are coalesced, and also all the threads that are in the same block are reusing using nearby data. Okay, and let's actually take a further look at it. Let me go back to the slide that we were on when we were writing the code. Okay, so this is the code that we just wrote. Okay, so data reuse in convolution. Now notice this thread over here, the thread that's processing this output element, okay, is going to use all of these input elements, right? But then if we look at what the next thread uses, so the threads in the same block load some of the same input elements. So if we look at what the next thread uses, the next thread uses all these elements. And as you can tell, there's quite a big overlap between the elements used by the thread that processes this output element and the elements used by the thread that processes this output element. Okay? So given this observation, what do you think we can do to capture this data reuse?
Coarsening?
Well, not exactly coarsening. What was the optimization that we saw before that targeted data reuse?
Tiling.
You could probably do coarsening to improve on it, but the main optimization for data reuse is tiling. Exactly. So what we can do as an optimization is if you look at the amount of the data that all the threads in the same thread block use, it's all this data over here. Okay, so this output tile over here uses this input tile over here. Okay, so an optimization that we could do is we can have each thread load one element of the input into shared memory so that the other threads can access it. So rather than having this thread load this element, and then this thread also load this element, and then this thread also load this element, we can simply have all the threads load this input tile into shared memory. So each thread loads one element. Okay, and then we can have these threads loop over the mask and loop over the input tile in shared memory and do the convolution operation. Okay, is that clear? Any questions about this? Now, if you can tell, there's a slight difference between this tiling and the tiling we saw in shared and tiled matrix multiplication. The tiling here, in the tiling here, the input tiles were as large as the output tiles. Oh, sorry, the tiling in matrix multiplication, the input tiles were as large as the output tiles. So we simply had every thread was loading one element in each input tile, and every thread was computing one element in the output tile. But in this case, the input tile is actually larger than the output tile. And in fact, if you take a look here, you have your output tile dimension, your mask dimension, your mask radius, okay, and your input tile dimension. okay? And the input tile dimension is actually equivalent to the output tile dimension, okay, plus 2 times the mask radius. So it's the input tile output tile dimension, which is this, and then you have the mask radius in this direction and the mask radius in this direction. So your input tile dimension is equal to output tile dimension plus 2 times mask radius. So your input and output tiles have different dimensions. So what do you do in this case? What can you do? We can't just have each thread load one input tile and calculate one output tile. The solution is, and what we can do is we can assign as many threads as we have input elements in the tile. So our thread block size is going to correspond to the input tile dimension. However, when we come to compute, we would only use some of these threads to calculate the output tile. Okay, so in other words, if this is our thread block, the dimension of our thread block is going to correspond to the input tile dimension. All the threads are going to be active when we are loading the input tile. Okay, but then after we load the input tile, only some of the threads are going to be active when we are computing and storing the output tile. So basically, when we have this mismatch between our input tile size and our output tile size, what we can do is we can over-provision the number of threads such that we have some threads that are only responsible for loading from the input tile without computing. And only a subset of these threads are used to compute. Okay, there's actually another way you could have done it. Another way you could have done it is you could have had as many threads as you have output tiles, and then have these threads that in the output tile kind of somehow loop over the input tile values and load them. Okay, but it turns out that that the code for doing that is quite complicated, and the performance benefit that you get is actually not that high. Okay. So for the next assignment, I'm not going to show you the code for doing tiled convolution, because for the next assignment, you will do it yourself. For the next assignment, you will implement code where you will launch as many threads as you have input tile, as you have elements in your input tile. You will use all those threads to load the input tile, and then you will use only some of those threads to calculate the output tile. Okay? Okay, so having said that, let's now analyze the compute to global memory access ratio of tiled convolution. So assuming that we implemented tiled convolution, let's now look at the compute to memory access ratio for tiled convolution. If we have an M by M mask, okay, what is going to be the compute to global memory access ratio for the non-tiled version? Let's start with a non-tiled version. So without tiling, if we have an M by M mask, okay, how many global memory loads do we have? For each thread, how many global memory loads does each thread perform if we have an M by M mask?
As many output pixels or output threads as we. Oh no, M squared.
Right, M squared. So every thread is going to load M squared elements from global memory. Let's take a look at the code again so that we can kind of verify that. So here you'll notice every thread, our global memory load is basically this axis over here. Okay, and every thread is going to do this load M squared times, and each one of those M squared times will be 4 bytes. So every thread is going to do M squared times 4 bytes of loading. And notice here that mask C does not count as a global memory load. So even though I have 2 operands here, only one of them counts as a global memory load because mask C is coming from constant memory. If mask C was coming from global memory, then this would be different. Okay, but here I only have this global memory load, so I'm going to do M squared times 4 bytes of loading. And then how many calculations, how many floating point operations does each thread do?
2.
Right, it does 2. It does a multiplication and it does an addition. Okay, and then there's M squared of that. Okay, so if I remove M squared from the numerator and the denominator, my ratio is going to be 4 bytes of loading 2, 1 plus 2 operations. So 2 operations per 4 bytes. That's 0.5 operations per byte. Okay.
But sir,
So
isn't it 4 operations?
Well, why do you say it's 4 operations? We have a multiplication and we have an addition.
Yes, but you also have in row times width plus column.
But we're referring to the floating point operations here. So look at floating point operations in global memory. Okay. Yeah. Otherwise, even this code over here is going to contain some integer arithmetic to calculate the address. But we're only concerned with floating point operations. Okay, so we have m squared adds and m squared multiplications. That's 2 m squared operations. We have, of course, here I'm ignoring the boundary conditions, right? So with the boundary conditions, threads will also, some threads might do a less than this, but most threads will do this. So the global memory loads per thread are m squared times 4 bytes. So 2 m squared operations over 4 m squared bytes is 0.5 operations per byte. Okay. Now let's look at the compute to global memory access ratio when we do tiling. Okay, so we haven't implemented the code for tiling, but we can reason about it, just by considering what it does. Okay, so with tiling, let's go back to the illustration. So here with tiling, every thread block is going to load how much global memory. Well, it's going to do input tile dimension times input tile dimension. Okay, and we said that the input tile is going to be the output tile plus the mask radius, plus 2 times the mask radius. Okay, and then the every output tile is going to do the block size times the block size. Okay, times m squared times m squared. Accumulations, and every accumulation is going to be a multiply and an add. Okay, so we have the tile size times the tile size times the mask radius times the mask radius times 2. That's the number of operations. And we have the tile size. The tile size times the mask dimension times the mask dimension times 2. That's the number of operations. And then the amount of data that we load is going to be the tile size plus the mask dimension minus 1 times the tile size plus the mask dimension minus 1. Okay, because the tile size by tile size is this. If I want to get the full input dimension, it's going to be the tile size plus the mask dimension minus 1. Okay, so here the mask dimension is 5, so mask dimension minus 1 is 4. So the input tile size is going to be the output tile size plus 4. It's 2 in each direction. Okay, clear where I got that from?
Professor, isn't it plus 2 times the radius?
Right, so 2 times the radius is the same as the mask dimension minus 1, right?
Yes,
so here,
right, yes.
2 times the radius is going to be 4, and mask dimension minus 1 is going to be 4.
Professor, can you repeat how the tiling صراحة ما فهمت.
Can I repeat what?
How did you number of operations for the tiling response?
Okay, so we're rather than focusing on what each thread does, we're focusing on what each thread block does, because some threads are only accessing data, they're not computing. Okay, so it's easier to think about what each thread block is doing. So each thread block is going to do how many operations? Well, I have tile by tile, so I have tile squared threads, or tile squared output elements, and for each output element, I'm doing m by m. So mask dimension by mask dimension. So mask dimension squared operations. Mask dimension squared accumulations, and each accumulation is an addition and a subtract, an addition and a multiplication. So I have tile size by mask dimension times 2 operation. And each thread block is going to load 1 input tile, and the size of an input tile is the size of the output tile plus the mask dimension minus 1. So I'm going to have tile size plus mask dimension minus 1 times tile size plus mask dimension minus 1 as the number of global memory loads, of course, times 4 bytes, okay, because each load is 4 bytes. Okay, so to summarize, we have if our tile dimension is t, if our input tile dimension is t. Oh, so here on the slides I'm doing it in terms of the input tile dimension. but it's the same thing. The final result is the same in terms of the ratio. So if my input tile is t, my output tile is t minus m plus 1. So my operations per block are going to be t minus m plus squared. Okay, this is the output tile, times 2m squared, okay, because I have m squared. So your t minus m plus 1 squared is my output tile squared, so the number of output elements I'm computing in the block. And then m squared is the number of mask elements that I go through for every output element. And 2 here is the 1 for multiplication, 1 for addition, okay? The number of global memory loads is going to be t squared times 4 bytes. So here, remember, t is my input size. So when I was talking to you on the image, we were working it out in terms of the output, but here we're working it out in terms of the input, which is fine. The ratio is going to be similar. So here we have t squared times 4 bytes. So the ratio is going to be kind of this operation, over here, t minus m plus 1 squared times 2m squared up over t squared times 4 bytes. So it comes out to 0.5 m squared into 1 minus m minus 1 over t. Okay. Now usually m minus 1 would 1 minus m minus 1 over t squared. Okay. Now usually m minus 1. So m is, if we have a mask of size 5, for example, this will be 4. T, for example, is if you have a 32 by 32 input tile. Okay, so you have something like 4 over 32, so it's 1 over 8. So 1 minus 1 over 8 is 7 over 8, 7 over 8 squared, so this number is not very, very small, okay? So depending on what m and t are, you'll have something that's, of the same order of magnitude as 0.5 m squared.
Professor?
Yes.
This operation is mainly done on images, so we can optimize for that. Instead of using floats, we can use integers, no? Which is one
right.
byte.
So you've basically redefined the problem, right? So if we have an image that if we're using this convolution on an image where the pixels of the image are represented in terms of 8 by 1 byte elements, then you're going to have a different compute to memory ratio. So of course, this 4 bytes is going to be in terms of your data type. Okay, but here I've defined the definition of the convolution operation that I presented was using floats. Okay, so yes, you can use characters, but that would just be kind of a different type of convolution as opposed to an optimization. Because if you really need to use floats because the operation you're performing is not an image but something else that you need to do a convolution on, okay, then you're going to use floats. You're not going to use 8-bit elements. But yes, you're right. If there's an image, then you could have used characters, and then when you do the compute to global memory access ratio, rather than having 4 bytes here, you would have 1 byte. And also, rather than having floating point operations here, you would have integer operations. Okay. Okay, so this is how we calculate compute the floating point operation to global memory access ratio. For short, I'm just using compute to memory ratio for the tiled convolution. All right. So here, like I said, for m equals 5 and t equals 32, this comes out to be 9.57 ops per byte. So this is around a 19 times improvement over the implementation without tiling. Okay, so tiling really helps you improve your compute to memory access ratio. And we saw the same thing before with tiled matrix multiplication. Over there, actually, we had even more improvement. We had when we used 32 by 32 tiles, we actually had a 32 times improvement in our compute to memory access ratio. Okay. One final comment about boundary conditions. When you do tiling, so like I said, we're not going to implement tiling in class because you're going to do that in the assignment. But when you do tiling, one thing you have to be careful of is, let's say you're computing this output tile, and for that you need to load this input tile. So when you load this input tile, there's 2 ways you can do it. You can when you load an input tile and then you start computing using shared memory, you can either go back and check if the original global memory access was inbound, or another popular way of handling these out-of-bound elements, which we also call ghost elements, okay, is you can simply load zeros in their place. So here, when I have this input tile that I'm loading, and I will load to shared memory, what I can do is the values that are inbounds, I can just load them as they are. The values that are out of bounds, I can simply place a 0 over there. And by doing this, what I can by storing a 0 in the out of bounds element, when I'm actually accessing the shared memory array, I don't have to worry about having a boundary condition anymore. The alternative would have been that when I'm going through my shared memory, I would also have had to have a boundary condition. But this solution tends to be a little bit simpler, where when you're loading to shared memory, you just load zeros for anything that's out of bounds. And then when you compute in shared memory, everything in bounds is a valid value. All right, and with that said, you can read more about today's lecture in chapter 7 of the textbook. And that is all. Does anybody have any final questions? Okay, well, if there are no final questions, then that's all for today, and I will see you next time. Bye, everyone.